So, thank you. Come on in. Miss Watson's our guest speaker.
Oh my
today.
God,
Clapping. Hey guys, I don't understand. You guys remember what I was saying?
Only if we were experimenting.
You recording it?
Yeah, she told me to.
Alright, when you guys are ready, we're going to start the first activity.
Woo!
Oh, I have it on my camera. Alright. Sure. Thank you for asking me information. Alright, dry ice. Let's read over the activity first, and then I'm going to explain it. We're going to play with it a little bit. Dry ice is frozen carbon dioxide. Carbon dioxide has the symbol, the element formula CO2. When it's added to water, it makes carbonated beverages such as soda. Dry ice is very useful in keeping things frozen because it has a temperature of negative 109 degrees Fahrenheit. It's pretty cold.
Oh, it's me!
What is happening? You're good.
Spirits in the room.
I'm just going to push you in the corner,
Okay,
and then
yeah.
we'll be fine. Alright, so...
Don't touch anything.
No, here, you can have a seat. You'll be my guest speaking, so over here for a minute. Okay.
Can we touch you in a chair?
Dry ice is pretty cold. Okay. Tonight's temperatures when you're going trick or treating, because I know all of you are, with your little siblings and stuff, I'm sure. All right.
I'm going as a yellow Power Ranger.
I'm going as a Chippendale.
Okay.
I'll be the guy with you.
Oh, I was thinking the chipmunks. Alright.
That awesome.
So, tonight's temperatures are going to be like 40 degrees-ish?
What?
50 degrees?
Like 55.
So it's going to be kind of cold. So you're gonna have to wear a jacket with that bow tie. Alright?
I don't want a jacket with that.
So think of it being 109 below zero. That's the temperature of frozen carbon dioxide. In fact, carbon dioxide, take your hands and go. You just made carbon dioxide fill your hands. If you froze that, that's dry ice. The cool thing about dry ice is that it changes directly from a solid to a gas through a process called sublimation. You know how like you have liquid water and it turns into a gas? What's that called? Think of the water cycle. It's called evaporation. So the process of going from a solid straight to a gas is called sublimation. All right. In normal conditions, it skips the liquid phase. That's why they call it dry ice, because there's no like liquid phase involved. So I have some back here. Oh, I need to have my actual bubble on.
Yeah, it might blow up.
Alright, have you guys ever played with dry ice before? Raise your hand.
Yep, my friend has.
Alright.
I played with mercury before with my bare hands. Does that say?
There's some safety stuff involved. It's cold, right? Okay, so you gotta protect yourself when you grab it. And otherwise,
Should I do? Should I go over there?
Alright, otherwise you get like instant frostbite. So, that's cool.
Check that somewhere.
Alright, so if you look at it, do you guys see the gas coming straight off of it?
Yeah.
Typically, if you take an ice cube and you put it out, like on the stove, what happens to the ice cube first?
Just melts.
It melts into like liquid water, and then after a while, it'll start like turning into the steam, right? So this one skips that whole liquid spot. It goes straight from like the solid to the steam. Okay? Well, it's not really steam, to the gas. Okay? So if I wanted to speed this up, I could put it in hot water and make it go faster. So that's what I'm going to do. Right. Oh, and the safety stuff is you never ever want to touch this with your like bare skin. I can feel it. It's really cold even through the glove. So I'm not even going to hold it in the glove for a long time. Okay? You would never want to like put it in your mouth because then you have frostbite on your tongue and that's sad. Right? Yes.
YOLO.
Only way colder.
I kind of want.
All right, so I'm feeling the purple today. So we're gonna do purple.
I really want to.
We need
Alright.
more.
And I'm gonna put the hot water in here, and then I'll put the dry ice in it, and you'll see it go faster.
Okay, touch the dry ice. I'm pretty sure if I like barely touch it, it wouldn't freeze my whole hand.
Hey Niles, pose, Niles.
Can I zoom in on this thing? Zoom it over your face, Gresh.
He doesn't want to zoom in on Gresh's face, bro.
Alright. So we got the hot water.
What are you gonna say?
Yeah.
No, I just put the here, I think it's it's queued up in the internet. Yeah. Alright, so put this in and hopefully it fits. Come on.
Lol.
Alright.
That's dangerous. I want to touch it.
Dude.
Isn't that cool? So it's just making it go from the solid to a gas faster because there's hot water involved.
Milk.
Wait, couldn't you like suffocate from doing
Alright,
that?
and if you were to like, I
What
don't
if you were
know.
to cover the lid? What if you covered the lid? I'm pretty sure it
So, look at the questions. How many carbon atoms are in carbon dioxide?
1.
1. Good. How'd you know? There's another thing after the C, so you know there's an invisible one there, kind of like algebra. Okay. How many oxygen atoms are there?
2.
Okay, so put them in there. All right. And then how can dry ice be useful? Think of some creative ways.
You can make fog.
Oh yeah, Halloween parties. This would look pretty awesome on your front porch. I'm just saying. You could also put it in your punch bowl for Halloween, right? It carbonates your punch, which is awesome because it kind of like turns it all bubbly like soda, and it makes it cold, and it bubbles up like it's in a cauldron or something. Yeah.
I was just one restaurant.
Oh, cool. Yes. Actually, it's kind of warm because I put really hot water in there. But it's been boiling for half an hour. Just hot.
And then let's go.
All right, and it's kind of fun too. If you put soap in it, then it traps all the gas inside of the bubbles. And then if you guys want to be my volunteers, anybody want to try it?
It's cold and I didn't even touch it.
All right, now pop the bubbles.
Oh, wow, man. You did it.
Wash your hands.
I'm good.
That's not as cool as I thought it would be.
Two things.
What?
And then, look out, don't touch it.
Just what I was thinking, like chemistry was way too bad.
Have you heard about the inspirational quotes in this one class?
Ah! Bubbles falling all over Christmas for days.
You don't see them.
She saw it last time.
Yeah, you were there.
Hitting it every 20 minutes.
You should put those on under the mask. Miss Watson. Maybe I will. You should put those like tumblers. I want some bubbles. Miss Watson, give some bubbles.
Alright, last calls because I want to do more fun stuff. Oh my gosh, really? Everybody? Ah, pumpkin.
Mother of pearl.
Oh, she got a lot. Pay for Sean. Pay for Sean.
Thanks, Greg.
Oh, that's so sick.
This is really fun to do with kids. Just don't. Okay, so just don't.
Shots fired.
Oh, dang it, dude. Alright, did anybody else want to
Hey, Sean. That's funny how it goes over.
What? Oh yeah.
It came up.
Alrighty,
Don't touch your face.
It's fine. Alright, here's the thing. If you put dry ice in your punch, you just gotta make sure that nobody scoops out the chunks of dry ice into their punch like cup, right? Because you just want to be careful that your lips and your tongue don't come in contact with it. It's so stinking cold. Okay. One time I took a giant block of it and just threw it in the jacuzzi, and then we went into the jacuzzi. It was really fun. It was like all over the place. You just keep your feet off the bottom and you're good. It would hurt you, yeah. Yeah. Grocery store, Smart and Final, it's like $10. $10 for a block of it. No, they card you.
But it's
They card you. You have to be 18. But if you're going to a party, you can just ask your parents to buy it for you. Like you just have to be really careful. Oh, by the way, if you notice, I have it in like a foam cooler instead of like a hard cooler, because if you have a container where it's like completely sealed and closed, then the gas takes up more space than the solid did and starts to get more and more and more pressure, and it like blows up. in your car. Okay, yeah.
So definitely do that.
It works faster with the hot water. You saw when I was holding it, it still did like the thing. So the hotter the environment, the more quickly it like changes. All right. So now next one, glow sticks.
Wait, what are
Alright.
the answers? Was it 1, 2?
You guys remember?
Don't do it.
Do you guys remember the flame lab? Oh, thank you very much, but do it nicely. All right, you guys remember the flame lab?
Yes.
What made the electrons jump up higher than they were?
Heat. They had heat.
The heat from the fire. My hot husband. All right, so it made the electrons jump up. Okay, so
On video.
Yeah.
all right, so the electron jumps up high. Oh, my film is like on the ceiling. Okay.
My bad.
If anybody watches it, they're gonna throw up.
It felt for like 2 seconds.
Okay. All right, so the electron jumps up out of its normal like spot because the added energy of the heat. All right, but how does it go back down? It has to release energy. What kind of energy does it release? What kind of energy does it release? Remember when we did the flame lab?
Light.
No,
Light.
no, not the flame. The flame is what caused it to go up.
Energy.
The energy in the form of light. It was colored light. So, like, depending on how far it was falling, it was a different color. You guys remember this?
Yep.
Okay, in the in the glow stick, it's the same thing. Only instead of being added by heat, because glow sticks don't get hot, instead it's used through a chemical energy. It's through the breaking and forming of new bonds. You guys remember in nuclear decay when the atom went through radiation and it split? You remember half-lives? You remember all that? Okay, when the atom split, what happened?
They got lost half of the line.
And what did it produce?
New one.
Why do we do this in like factories? Like, why do they split atoms in factories? What's the whole point? What are they trying to get from it? Energy, lots of energy. So when the atoms split and they like take apart their bonds, then they get all this energy and the electrons go whoop from all the energy, and then when they release that energy, it releases it as light. So if we read this part, this is kind of like a summary, okay? Only instead of heat now, it's chemical energy from the breaking of bonds. So here we go. The reaction between the different compounds in a light stick causes a substantial release of energy, just like in nuclear reactions. Just as in an incandescent light bulb, atoms in the materials are excited, causing the electrons to rise to a higher energy level and then return back down to their normal levels. When the electrons return to their normal levels, they release energy as light. This process is called chemiluminescence. Try it.
Chemiluminescence.
Try it again. Try it 5 times fast. It sounds like you're doing it like an incantation. All right, it's kind of creepy. All right.
Like raising someone from the dead.
Just take it way creepy.
Wait here.
All right.
Okay, we're like right here. We're like
All
right
right,
here.
all right, all right.
Come on.
Second paragraph. We can get through this. Come on. All right, come on. The chemical reaction in the light stick is usually involves several different steps. The typical commercial light stick holds hydrogen peroxide inside it. You guys ever use hydrogen peroxide in cuts? And like bubbles up and it stings like bleh, you know? So that's the kind of stuff, only the stuff that you're putting on your cuts is only like a little bit hydrogen peroxide and the rest water. So this is like severe hydrogen peroxide. And it also has a solution containing a polyoxalate ester and a fluorescent dye. So if you remember, I told you before that a light stick has the plastic part, which has the chemical. So I already broke open the plastic part and dumped out the first chemical. And then there's a glass tube on the inside that's containing the second chemical with the fluorescent dye inside. Do you guys remember this from before? Okay, so once those two chemicals mix, then that process is going to be like going through. So here's what happens when those two mix. The hydrogen peroxide oxidizes the phenyl oxalate ester, releasing a chemical called phenol and an unstable peroxatic ester. The unstable peroxatic ester decomposes, resulting in the additional phenol and cyclic peroxy compound. The cyclic peroxy compound decomposes to carbon dioxide, and this decomposition releases energy to the dye. The electrons in the dye jump up to the higher level, then fall back down, releasing the energy in the form of light. Fancy way of saying, when you break apart compounds, they get energy. The energy goes to the electrons fall back down, releasing that energy as light. Do you want to see it? Lights, please. Oh, let me put on gloves. Have you guys ever seen the show Firefly?
Yep.
Yeah.
2x2 with hands of blue. Okay. Alright, so I'm going to break the glass and release the chemical into here. And I'll turn glass. What, broken glass? Or this stuff? It's slightly toxic. Hey, it's going on my gloves. Alright? So, can you imagine the little electrons falling back down and like releasing their piggyback partner of energy of light? They're like, bye! And they fall back down. Alright? Do you want me to put this in with the dry ice?
Yes.
Alright, let me go get some dry ice.
Sweet.
Pardon-moi.
Susie?
I don't mean to be filming that. What? Oh!
You guys seriously gotta move your backpacks. Okay.
Don't miss.
I know.
Psychedelic.
Okay, that seriously looks cool. Look at the side with the glowing bubbles.
Whoa.
Okay. So now. Oh yeah, you guys have to answer some questions. Turn the lights on. Turn the page over.
Psychedelic, bro. Gnarly.
Alright, here's some questions for you. Whoa, go.
It's like shooting.
Okay. As the glow sticks, are the glow sticks an example of a chemical reaction or a physical reaction? Raise your hand and tell me what you think. Evan.
Chemical reaction?
Why? Good.
Because it's like different chemical elements are like forming daily.
Fantastic. I like your explanation. Other evidences of a chemical reaction.
Using chemicals.
I am using chemicals. But why do we know it's a chemical reaction?
It's called Chemiluminescence.
Yeah, that is a clue.
Color change.
Color change. You guys remember all these clues?
Yeah.
Color change was one of them. What was another, Bean?
Transfer of energy.
Great. It's producing that light, which is a transfer of energy.
Temperature.
Yes, the temperature, well, sort of. It didn't really change, but it can change. All right. Is it a physical reaction? Did I have to do something physically?
Yeah.
What did I do?
Break it.
I broke the glass, right? So it's kind of both. As long as you explain both, you're good. And then what causes the glow stick to release that colored light? Yes? Yeah.
The electrons jumping.
And when they come back down, they release the light. All right, so you can even draw a little picture if you want to. Only don't put heat on the side because this one isn't about heat. What's over on the other side? Yeah, the breaking of the bonds, the chemical energy. Okay, so now, because I feel like it, we're going to light a pumpkin on fire.
Yeah.
All right. So one of my best friends, her name's Sarah, she carved this pumpkin beautifully in like kind of like a dragon. Does anyone recognize this dragon picture? It is the Jabberwocky, and so that's why I invited Miss Watson to be our elegant special guest. And she is going. Listen. She is going to recite the Jabberwocky poem.
Recite? No, I'm not.
Oh, what's the
read it.
difference?
I rise.
I don't know.
If I could memorize it for you, and someday I will, then I will recite it.
I can't even read the thing. There are so many made-up
It's hard
words.
to read.
Okay. So I'm gonna in my friend's honor, I'm going to light this pumpkin on fire while Miss Watson is reading the Jabberwocky poem. So hold on just a minute. I gotta get this all ready.
Welcome to the
Once I touch.
Do you get like expelled for saying that?
Whoa, what are you doing?
And just in case, I took out the fire blanket and it's sitting right next to the table.
So if she catches the fire,
Yes, it is.
fire blanket.
Yeah, Brady, you gotta get it.
Oh, thank you.
Put your socks on it.
Maybe you're in charge of the fire blanket.
Wait,
I have to be. You're to jump on it.
Dude.
And
Oh yeah, this makes it burn like purple or green. Oh my god.
That thing must be like.
alright, so I hope that's enough because last time it didn't light on fire. So let's see if it works. And then because we did the flame lab, thrown in some copper. So what color will the flame be?
Blue.
Oh! Green. And some lithium. Do you guys remember what lithium makes?
Pink. Purple, pink.
Like red, purple, pink?
Yeah.
Smells good.
Alright. So if it doesn't work, I'll light the little one because that one does work. And then I'll just put dry ice in this one if it doesn't work.
Oh,
Alright.
sweet.
It's right there by the exit. Do you want one? No.
Hold on. Gotta get my
I know
phone out
where
too.
It really isn't as dramatic as it sounds.
Lights.
It's not really lighting. See, it's not doing it. I don't know why this pumpkin is like resisting.
You put hand sanitizer.
And then I wonder how forest fires get lit on accident. It's like
We're really trying here.
Seriously?
No.
See, it kind of lights, but then it doesn't. Can you turn the lights off at all?
Yes.
Oh, I see something inside.
Oh, is it on fire?
Yeah. It's green and
So it's got the green and red flames. Okay, Miss Watson, please read.
The
All right, listen up. You have to be
Jabberwocky.
respectful of poetry. Here we go.
Thank you. The Jabberwocky by Lewis Carroll. 'Twas brillig in the slilthy toves, did gyre and gimble all a wobby. All mimsy were the borough groves, and momy raths out wobby. Beware the jabberwock, my son, the jaws that bite, the claws that catch. Beware the jub bird, and shun the frumious bundersnatch. He took his vorpal sword in hand, long time the maxim foe he sought. So rested he by the tum-tum tree, and stood a while in thought. And in an uffish thought he stood, the jabberwock with eyes aflame, came whiffing through the tugly wood, and burbled as it came. 1, 2, 1, 2, and through. The vorpal blade went snicker-snatch. He left it dead, and with its head he went galumping back. And hast thou slain the jabberwock? Come to my arms, my beamish boy. Oh, frabjous stay, callooh, he chortled in his joy. 'Twas brillig in the sliffy toves, did gyre and gibble in the wobby. All mimsy were the borough groves, and momy raths out wobby. Snaps.
Oh, snap. Snaps to Miss Watson.
The Jabberwocky.
All right, thank you very much.
Thank you.
On one PM.
Yeah, do you want to see the little one? Because the little one actually lights on fire on the outside.
What was the sound, dude?
Wait, is that all it's supposed to do? The big one? Mrs. Peterson? Is that's all it's supposed to do?
Well, that's why I put it on the outside to see if the big one would light on the outside. But I think because it's such an old pumpkin, it's like 2 weeks old, something like that. I don't think it really lit. All right, so we're gonna do the little one. Oh, it's still glowing. Look at that. That's kind of cool. All right, a little bit of lithium. Oh, that was a lot of lithium. Alright, and gasoline. It's not gasoline.
So where do we get these, what is it, gasoline? Where do we get these elements so I can light my house?
You don't.
Can I borrow some?
Alright. You're stealing away, people.
Oh, stop.
Not too far.
Wait, you didn't do that to the other one.
So I got like a sick angle.
No, the other one wouldn't light.
So it kind of does the outside, but I don't know how to do it better on the outside. I'm still learning. This is my second day with this kind of thing. Alright, so I carved that one. Can you tell?
It's beautiful.
Thank you. Alright, not too close, guys. Let's get back. Are you doing a selfie with the pumpkin on fire?
Oh, it's on a selfie.
Whoa. Alrighty.
Wait, I didn't have flash on.
Alright, lights, please. Thank you very much. Alright, it is now time for us to watch some professionals. Alright, at the University of...
Should I stop
Miss
it?
Watson, say thank you again.
Bye. Should I stop it?
No, no.
Alright.
Oh, actually, yes.